for instance, a chi-squared fit, and this is a result of this fit. So you will find one preferred region which is in the vicinity of the standard model, and also another region where basically you flip the sign of the coupling of the Higgs to the fermion, in particular to the top quark. And this has an effect on the decays into gamma-gamma. So as I was saying before, the decays into gamma-gamma is only a loop-level process in the standard model, and there are two loops that enters in this decay. There is a loop of W and a loop of top quark, basically, plus some smaller loop like a loop of the bottom quark, etc. But they are negligible in the standard model. So now in the standard model, the loop of the W and the loop of the top are actually of opposite signs. So namely, you have a negative interference between those two loops. So now, if compared to the standard model, you flip the sign of the coupling of the Higgs to the top quark, then you flip the sign of the loop of the top quark, and you will get a positive interference. So this means that by flipping this sign, by flipping the sign of C, right, you will get a positive interference, and then you will increase the decays into gamma-gamma. So that's a way basically to reproduce the enhancement that seems to have been observed by ATLAS and CMS. So that's why, in a sense, there is this other region, the negative value of C, which is also preferred by the data, by the current LHC data. So now what will happen with this gamma-gamma access, nobody really knows, or nobody is allowed to tell you exactly. But even if it goes to the standard model value, so even if gamma-gamma decays goes to 1, then basically you will still find another region in this parameter space which is basically degenerate with the standard model points. Yeah. So there is a degeneracy in this parameter space in the coupling of the Higgs, something that the current LHC data cannot basically resolve. So this kind of analysis has been performed by various groups. Actually, here I've reported several plots that I found in theory papers, and they all basically agree with each other. There is always two preferred regions, one in the vicinity of the standard model, and another one with a negative coupling to the top quark. And finally, this kind of analysis has been also reported by the experimentalists. Here there is a plot by CMS and another one by ATLAS, and they basically agree with each other and reproduce also the feed that were done by the theorists, neglecting many details of the signal. Of course, so for instance, the theorists don't have access to the correlation between the various channels. They don't have access either to the various composition of the various channels. So namely, when you look into gamma-gamma, so you put some cuts to isolate the various production mode of the Higgs. But of course, even within these cuts, you still have a lot of contamination between the various production modes, and the exact composition is still something that the experimentalists keep secret and don't report openly. So it's difficult to really perform a fully consistent analysis. Right? Nonetheless, you can check on this plot that the details, all these details don't matter a lot, and you basically agree with the various contour lines that you can obtain in this chi-squared fit. So that was the first example of analysis that were performed. So basically, we wanted to check if the Higgs is really there to unitarize WW scattering or not. But there is also other things that you can check using the current data. So for instance, you can check whether the Higgs satisfies the custodial symmetry. So namely, whether the deviation in the coupling of the Higgs to the W is equal to the deviation of the coupling of the Higgs to the Z gauge boson. And of course, this is very important if you want to be consistent with all electric precision data. For instance, if those two deviations were not equal to each other, then at one loop you will generate a huge contribution to the T oblique parameter that is in conflict basically with the lap measurement. So basically, testing this relation is a way to see if the LHC data are consistent with the lab electric precision data. Then you would like also to see whether the Higgs actually respects the weak isospin symmetry, so namely whether the deviation in the coupling of the Higgs to the up-type quark are the same as the one in the down-type sector, down-type sector, whether there is a quark-lepton symmetry or universality, so namely if the deviation in the coupling of the Higgs to the quark are the same as the deviation of the coupling of the Higgs to the lepton. And finally, you would like also to see if there is possible new physics contribution to the radiative decays, right? So for instance, if there is new particle that run into the loop for the decays of the Higgs to 2 photons or the gluon-gluon fusion. So basically, whether there is any new additional contribution to the contact operators between the Higgs and 2 photons or 2 gluons. So as I say, I mean, you cannot test simultaneously all these properties, but one by one, you can test whether or not they are satisfied. And here, for instance, I've taken 2 plots that were shown by ATLAS in a publication last October, last fall. And basically what you found is that while there is some consistency with the standard model, there is a little bit of tension. So typically the standard model is something like 2 sigma away from the best fit point, but none of those deviations are statistically significant to see that we have really identified some physics beyond the standard model at the moment. So one important question that we want to address, and that is not done yet, is the following. We want to ask whether the Higgs is really part of a SU2 doublet, which means, in a sense, whether or not new physics, if there is new physics beyond the standard model, actually, if this new physics really flows towards the standard model in the infrared. So namely, whether the standard model is really or not a good infrared description of this new physics. And for that, of course, the Higgs will have to be part of an SU2 doublet. So namely, you will have to combine the Higgs boson together with the longitudinal component of the W and the Z to form a doublet under the SU2 symmetry. So the way to test that is now basically to write a chiral Lagrangian in terms of higher dimensional operators using this Higgs doublet, right? So this is a task that, classification of those operators is a task that started many years ago, mostly by this pioneering paper by Burkmuller and Wheeler in '96. And if you open their paper, they had a lot of operators, about 80 or 90 of those operators. And actually, many of those operators are actually redundant. Namely, you can get rid of them by doing some field redefinition. And actually, a complete classification only appears a few years ago by this paper from Warsaw, from the group in Warsaw, where basically they really, for the first time, they really introduced a minimal set of operators, which is not redundant. And there is about 59 of those operators. Nonetheless, not all of those operators are important for the physics of the Higgs boson. And you can also eliminate some of the operators, assuming, for instance, that you have a CP invariance. And also, some of those operators cannot be generated at tree level by any new physics. They can be generated only at the loop level. So, namely, you expect that those operators will be suppressed. Right? So this is basically a list of those operators that really matters for the Higgs physics. And you can count that there is basically only 14 of them that can really affect the Higgs physics at tree level, for LHC physics. So now to come back to the question whether the Higgs is part of a doublet or not, to answer this question, actually, you will need to look at processes that involve more than one Higgs boson. Because this is the only way really to be sure that the Higgs is forming a doublet, and then that you can see really the SU2 structure. So the various process that you want to probe is double Higgs production by gluon fusion, where basically in this case you will be sensitive to this new interaction that doesn't exist in the standard model, which is an interaction between 2 top quarks and 2 Higgs bosons. So of course in the standard model you do have double Higgs production by gluon fusion, but it is mediated by actually the Higgs self-interaction. So namely, you have a loop of top quark, it produces one Higgs boson, and this single Higgs boson actually decays into two Higgs boson via the Higgs self-interaction, the Higgs cubic interaction. While here, you have a new diagram, this new diagram that is shown in this slide, and this new diagram actually enhances this production cross-section by 1 order of magnitude, typically. So basically, this is something that you can test again at the LHC once the luminosity will be increased. So typically, when you will be running at 300 inverse femtobarn, you can already say something about the existence of this new coupling. Then the other interesting process to probe, whether or not the Higgs is part of a doublet is to look at WW scattering producing two Higgs bosons. So basically double Higgs production by vector boson fusion. And here again, if the Higgs is part of a doublet, this quadratic interaction between two Higgs and two W is related actually to the linear interaction by this kind of relation. So B is this quadratic interaction is related to the squared of the linear interaction. So it's again the prediction of the standard model. This relation is also true actually even if you have deviation compared to the standard model, but if the Higgs is a doublet, this relation will hold in general. While if the Higgs is not a doublet, for instance, if the Higgs is actually a dilaton or something like that, right, then there is a priori no relation between the quadratic interaction and the linear interaction. There is also a third process that could be very interesting, which is a triple Higgs boson production by vector boson fusion, because again, you will test, the existence of a new interaction beyond the standard model, which is this new vertex here. And again, if you have this vertex here, you can get a tremendous enhancement of this cross-section, something like 3 or 4 order enhancement compared to the standard model prediction. So basically, this process could tell you immediately if the Higgs is really, has really this structure. So if you look and can see this particular production mode, this means that this new vertex will be present in your theory, which will point towards model, for instance, where the Higgs is a composite object. Okay, so having an effective theory is good, but what you would like to understand also is the relative importance between the various dimension 6 operators that control the physics of the Higgs boson. And for that, you need to put some dynamical assumption. And here, I will propose a very simple dynamical assumption that can interpolate between weakly coupled model of electric symmetry breaking and strongly coupled models like those composite Higgs objects. So the dynamics is really assuming that you have the standard model sector, which is characterized by the weak scale and the standard model gauge interaction, plus maybe the top Yukawa interaction. And then all the standard model degrees of freedom actually have a mass mixing with a new physics sector, which is characterized by a mass scale, capital M, that I will rewrite as a typical coupling of the new physics sector, G star times F, right? So if you want, you have to think in analogy with QCD, with M rho, which is equal to G rho times F pi, the decay constant of QCD. But it can also be a weakly coupled sector, like in supersymmetry, for instance. And then in this case, G star, or G rho, if you want, will be of the same order as the coupling of the standard model. Then those two sectors simply mix with each other, so there will be a mixing which scale like G standard model squared divided by G stars, the typical coupling of the new physics sector. So one important question is to understand whether G star is weak or whether it is rather large, like in QCD. So this will differentiate between model of electroweak symmetry breaking like supersymmetry or model like composite state, a composite Higgs model. So So the power counting is very simple, actually. So in all these dimension 6 operators, every time you add one power of the X field, it has to be suppressed by the scale which is which is f, and every time you introduce an extra derivative, it has to be suppressed by the mass scale of new physics, capital M or M rho, etc. And of course, in this case, if the coupling of the new physics is large, then M rho will be much larger than F. So this means that all the operators with additional derivative will be further suppressed compared to the operators that involve extra power of the Higgs boson. So the classification is rather simple in this case. There is only 4 operators actually that are suppressed by the scale F or F squared. And there is this operators that correspond to 2 derivatives and 4 power of the Higgs field. Then there is some modified Yukawa interaction, and there is modified Higgs self interaction. And in the coupling that in the operators that involve extra derivatives, there is also some hierarchy in the factors that suppress the different operators. So for instance, if you look at the second line here, and write those operators in the unitary gauge, you will notice that those operators will give rise to a coupling between the photon, the X, and the Z gauge boson. So this means that this operator gives rise to a coupling between the photon and 2 neutral objects. Of course, such a coupling cannot occur in any theory that satisfies minimal coupling. If the photon satisfies minimal coupling, then the photon at tree level can only couple to object that carries an electric charge. So this means that in any theory that satisfies minimal coupling, those operators can only occur at the loop level. So that's why there is a loop factor that suppresses the coefficient in front of these operators. This is also true for the contact interaction between the X and the photon and the gluon. They cannot occur at tree level, so you certainly have one loop suppression factor. And you could even have a further suppression if you assume, for instance, that the X is a Grojean boson. So you know that in the standard model, the longitudinal component of the W and the Z are a Grojean boson associated to the breaking of SU2 left cross SU2 right broken to SU2 diagonal, the custodial symmetry. And in many interesting model of new physics, the Higgs boson itself is an additional 4th Grojean boson, right? Associated to the breaking of a bigger global symmetry. So for instance, you can embed SO4, or if you want, embed SU2 cross SU2, SU2 left cross SU2 right, into SO5, and break SO5 down to SO4, and this produces exactly 4 Grojean boson. So in these models, really the full Higgs doublet appears as a Grojean boson emerging from a spontaneously broken global symmetry in the new physics sector. So in this case, those operators, those contact operators, that involve some non-derivative interaction of the X can only occur via some interaction that are breaking the global symmetry. And those interactions are typically the standard model interactions themselves. So that's why those two particular operators are loop suppressed, but loop of a standard model interaction. And of course, if G is smaller than G star, the typical coupling of the new physics sector, then those loops will be smaller than the previous loop that I was talking about. So this power counting really gives you a very precise scaling of the different operators that are relevant for the Higgs physics. And at the end of the day, you can count that there is one operator, like this one, 3 operators for the different type of fermions, and there is a Higgs self interaction, but this doesn't play any role in the standard model. And all the other ones will be further suppressed and basically don't play any role at the moment at the LHE. Maybe in the future we will have access to those ones, but at the moment, when you are only sensitive to those strong operators that are suppressed by the scale F and not by the scale of new physics. Yes, there is a question? Yann?
Yes.
You have to do some. Yes, I think there is a question from the CERN group, right?
Yeah,
As far as I can.
He has to accept it. You have to wait a little bit.
Okay.
You can speak now, I think. Yeah.
Belen, okay.
Belen.
I think it was
I think your microphone. Belen, we don't hear you, Belen. Belen. You have to make something with the microphone. We don't hear you, Belen. No, Christoph, you understand what she's saying?
No, no.
No, okay, Belen.
Belen,
Belen, you
yeah,
microphone, Belen.
can you write the questions? Johanna, answer again.
Okay, good.
What are these models different? Okay, so I mean, here it's really a full classification of the different operators. So yeah, maybe I can ask, I can repeat the question. So Belen was asking in which sense this classification is different than the one or the model proposed by Manoa and Grojean in the 80s. Well, here it's really a full classification of the different operators with a particular power counting. And, you know, understanding, for instance, that there is those operators that are loop suppressed, for instance, because there is minimal coupling, etc. That's something that was not taken into account in the previous analysis. So here, the point was really to identify, you know, how many operators are relevant for the physics of the Higgs at the LHE, and which operator are only giving you some correction to the dominant effect.
So Belen had that the idea, basic idea is the same. The classification not.
You know, yeah, so here the issue is really that there is a hierarchy of scale suppressing the different operators. So while in the first classification, basically we're assuming that, you know, you have strong interaction, so 0 is equal to 4 pi, and then clearly you don't see these loop suppression factors anymore. Right? If 0 is equal to 4 pi, then this loop suppression factor becomes of order 1, and then you don't see this particular suppression. While here you have really an interpolation between weakly coupled model and strongly coupled model. So if you want this power counting is valid whether you are dealing with a weakly coupled interaction or strongly coupled model where 0 can be bigger than 1 and still smaller than 4 pi. If you want the old analysis, we're missing really these subtleties of the loop suppression factor coming from the new physics interaction. And I think they were also missing, you know, the possibility that the Higgs is a Gaussian boson. So this additional loop suppression factor for the operators that are controlling the decays into photon or gluon. You know, in the past, people used to say that the best place to look and test for new physics is to look at the decays into gamma gamma and blue blue. So they were implicitly referring to those two operators. But actually, in model where the Higgs is a Gaussian boson, then those two operators are highly suppressed, and the dominant effect are really coming from those operators that are suppressed by the scale f, and not by the scale m rho.
So Brian said that they did loop suppression too, Grojean and Manuel.
So which loop suppression? The loop of the new physics sector or the loop of the standard model suppression?
He's typing.
Okay. Yeah, okay, yeah. No, the idea, of course, the idea of Higgs being a composite object is not new at all. And in here, but I mean, if you want, in the past, people didn't have this effective description in mind. So they didn't have this classification of operators that really affect the physics of the composite Higgs object. So they were more like trying to find an explicit model.
Good. You can go on.
Okay, whatever. So having this power counting, okay. Having this power counting basically really give you, the different scaling of the Wilson coefficient that suppress all these dimension 6 operators. So to answer to Alvaro, of course there is additional operators that I haven't written here that basically control the interaction. I mean additional operators like co-Fermi operators and things like that have no effect, of course, on Higgs physics, except basically modifying the backgrounds. But at the moment, I think the current constraint coming from flavor physics, etc., on these 4 Fermi operators is telling you that this modification of the background can be totally neglected, and there won't be any effect. So we have identified this particular scaling of the various operators, and of course, in addition of this power counting, you could have some specific selection rules. So, for instance, if you take the MSSM, you could also generate, at least in the decoupling limit, when the scale of this additional charge X or CP odd X, etc., is much larger than the mass of the X that we are interested in, then you can integrate out all these additional degrees of freedom and again obtain a very similar effective Lagrangian. Except that in SUSY you will have some selection rules, and for instance you will not generate this CH operator at the dimension 6 level. It's simply, I mean, actually it's very generic. In any 2x doublet model, CH will be equal to 0. It will only, I mean, such an operator could only occur at dimension 6 and not at dimension 8 and not at the dimension 6. Right? And as I say, if you further assume that there is that the X is really a pseudo-Goldstone boson, then there is a further suppression of some of those Wilson coefficients. So now, in the next couple of slides, I wanted to show explicitly what are the effects on the physics of the Higgs boson from those various operators. What are basically the parameters that modified all the production mode and the decay branching ratio. And I will start with this operator that are suppressed by the scale f, and you can see actually that all those dimension 6 operators that are suppressed by the scale f actually give you some correction to the Higgs coupling that scale like v squared divided by f squared. So that was true, for instance, in the previous, I mean, to make the connection with the previous Carrel Lagrangian that I was describing. So the modification of the coupling of the Higgs to the gauge boson at the p squared level, they will get some correction that scale exactly like v squared over f squared compared to the standard model prediction. And this is also true for all the coupling to the fermion and also for the Higgs self-interaction. If you look now at the operators that are suppressed by the mass scale of new physics, M rho, capital M in the previous description, you can see, you can convince yourself actually that they give rise to modification to the inclusive rates that scale like the mass of the W divided by the mass scale of new physics. And of course, this is in principle a smaller modification compared to the previous operator that we discussed. There is also an interesting contribution actually to the off-shell decays into gauge boson. So when the X decays into W star or Z star, you know that in the standard model, this is mediated basically by an off-shell W or off-shell Z, right? Which effectively appears as a free body decay. So you have a 1X that decays into 2 leptons plus 1 on-shell W or 1 on-shell Z. But in this case, those operators actually give you a contact contribution to these decays, and this means that you will have different distribution to the two fermions. And this is actually an analysis that were performed, I think, quite generally by people like Alvaro and his CMS colleagues. And basically now you can reuse all their analysis to really put some bounds on these dimension 6 operators. Right. So by really looking at distribution instead of looking at the inclusive rates for these decays. And then finally there is the loop suppress operators. So the loop suppress operators into WW. And here, clearly, since they are loop suppressed, they won't compete at all with the previous effect that I was describing before. So the only way to have access to those operators is actually to look at the decays into gamma and Z, where indeed you find a modification of the amplitude that again scale like V squared over F squared compared to the standard model amplitude. So here you are really testing the, if you want, the coupling of the new physics sector. As for gamma gamma, again, in principle, there is a correction that scale like V squared over F squared, but again, in principle, you have a loop suppression factor if the X is coming as a pseudo-Goldstone boson. So the conclusion is that if the X is not a Goldstone boson, then the decays into gamma gamma allows you to test these operators. If the X is a Goldstone boson, like in those composite X model, then the decays into gamma gamma is not the good process to probe these operators because of this additional suppression, which is the ratio of the coupling in the standard model divided by the coupling of the new physics sectors. Okay, so now moving a little bit further, so all these previous estimates were based basically on the power counting of all the Wilson coefficients at the scale of new physics. So basically integrating out the new physics degrees of freedom, you obtain some Wilson coefficient at the scale of new physics. But of course, in any physical process that involves this Higgs boson, any of those processes occurs at a much lower energy. So this means that you have to run down your effective Lagrangian. So you have to take into account renormalization group evolution from the scale of new physics, capital M, to the weak scale, scale mu, let's say, which could be the mass of the X or, let's say, the mass of the top, etc. So you have to take into account some loop effect that, or if you want, you have to compute those anomalous dimension of this Wilson coefficient. So the dominant effects are, of course, coming from the loop of strongly interacting degrees of freedom, in particular the loop of the Goldstone boson, that have a coupling that scale like G star and not G weak. So here I've represented a few of those loops. For instance, they could give you anomalous coefficient from the operators that were tree-level operators like CH or CW plus CB, down to operators that were loop suppressed like CHW and CHB, right? The one that give rise to H to gamma Z, for instance. So we have computed those anomalous dimension. In particular, there is one which is non-vanishing here. There is a lot of zeros in this matrix of anomalous dimension, but there is one which is non-vanishing and give rise to interesting effect that I will describe in a moment. So now, you see that this anomalous dimension can affect actually the power counting, because you have the power counting which were estimating the value of this Wilson coefficient at the scale of new physics. And finally, you can have the log contribution, which is coming from the running, right? And the log, which is also mixing the different operators. So for instance, you can look at the mixing of CH operator into CW plus CB, which is just the S of oblique parameters. So here at tree level, you have a contribution that scale like the mass of the W divided by the mass scale of new physics squared. And indeed, this is always larger than the loop contribution, because here you have a loop suppression factor. But the case is different when you are looking at the mixing of CH into an operator which is loop suppressed at the new physics, at the scale of new physics, right? So if you look at CHW plus CHB, this was loop suppressed. So you have this loop suppression factor of new physics. And in this case, the mixing coming from CH can be dominant and can be log enhanced compared to this tree-level contribution. So this means that you cannot neglect this running effect. There is also very interesting renormalization group evolution effect into the decays into gamma-gamma. So as I was saying before, there is this particular P to the fourth operator that give rise to tree-level decays of the X into gamma-gamma, but all these P to the fourth operator were actually generated at the one loop level for the reason that I've said before. But now, because of the mixing, with operators that can be generated at tree level, you can indeed get, some sizable effect from other operators. And that's exactly what I reported here. The mixing from CW plus CB actually give rise to gamma-gamma at the low scale. And you can see that this effect here can be log enhanced compared to the previous tree-level contribution from the previous contribution that were obtained at the high energy scale. So this means that you have to take into account this logarithmic running. Okay, so as an example of this mixing and the renormalization effect, you can actually look at the effect of the operator that... Yes, there is a question? Okay, go ahead. People in Madrid.
Yes, the voice, no mind. Enrique?
Hello?
Yes.
Are you listening to me?
Yes.
Hello? Yes?
Yes.
Can you listen to me correctly?
Yes.
Okay.
Yes.
No, I was wondering if in this interesting analysis you are now explaining about the renormalization group statistics, could it happen that the coupling you mentioned at the beginning of the talk of the Higgs to the top can change the sign due to these renormalization group equations? I mean, the running due to new physics, your language? Could it be?
So flipping the sign of the coupling to the top actually can be obtained simply by some X nonlinearity. So I mean, I don't think it can be generated by this running, but it's simply coming from this additional modified Yukawa interaction that I was presenting before. I was saying that in the standard model you have Yukawa interaction that involve only a single power of the X doublet. But at the dimension 6 level, you can add, of course, extra power of the X doublet. So, for instance, there is an operator that involves 3 power of the X boson. And then, if you expand this operator in the unitary gauge, actually, you will get a modification of what is called the Yukawa coupling. So, this parameter C or CT that I was describing before. So, by playing basically with this modified Yukawa interaction, you can actually get some negative coupling of the X to the top quark. But I don't think you can really get it from the running that I was describing here.
Yeah, but one
so
could think the complex way of deriving that. I mean, you put these higher order dimensional operators into an effective coupling of the Higgs to the top, I'm sure that you can draw at some level of perturbation theory, in this approach we were explaining, a contribution to, say, a renormalized Higgs coupling to the top. So there is no impossible.
No, I mean,
it's not easy, but it's not.
So, I mean, first of all, so this particular anomalous dimension hasn't been computed yet. So the one that you are referring to, so that will be the mixing of some operators into CT. So this one hasn't been computed, but I don't think it can give you some very large effect that like the one that you need. So 100% effect basically in shifting the coupling, simply because you will need a very large log, you know, to have some sizable effect. But if the log is large, this means that the scale of new physics is very large. And since all these operators will be anyway suppressed by the mass scale of new physics, if the scale of new physics is very large, all this effect of this dimension 6 operator will be suppressed.
Okay.
So the conclusion is that this renormalization group evolution effect can give you something like 10% correction, but they cannot give you 100% correction because you know, to get 100% correction, you will need a very large scale of new physics,
Okay.
which is not possible. So yeah, so what I wanted to say is that, I mean, a concrete example of this renormalization group evolution effect is actually the mixing between CH that basically controls the deviation of the coupling of the X to the W and the Z, and the S parameter that has been measured by LEP. So here again, there is the same anomalous dimension, and indeed CH has an anomalous mixing with CW plus CB, which is nothing else than the S oblique parameters. So this means that, you know, if at the scale of new physics you generate CH, then by the running you will generate S oblique parameters at the scale of at the weak scale, basically the scale which is probed by LEP and LHC. So this way, using LEP data, you can basically put some constraint on the deviation of the coupling of the X to the W and the Z. And basically, the way to understand it is to see that explicitly you have a log divergence which is cancelled by additional new state at the scale of new physics. And you can probe basically, you can use this equation to combine the LHC data together with the LEP data to perform and see exactly how the fit of the coupling is changing, and the effects are quite dramatic. For instance, this was a fit only of the LHC data. And you see here that, you know, you were some deviation of the order of 20 or 30% for the coupling of the X to the gauge boson were allowed. But if you combine together with the LEP electroic data, then you are really restricted to correction below 5%. Right? So the picture is really changing dramatically when you are combining LEP with LHC. So, you know, there are some effects that have to be taken into account, and this effective description is really the wide description to combine basically the different experiments together, because you can see how the different measurements are correlated by using the renormalization group evolution. So I see that I'm running late. There were a few questions, etc. So I don't know, maybe I don't have time so much to discuss the implication for the early universe, basically the question of stability and triviality, etc. So I can leave it out. I wanted also to discuss more specifically the implication of the measurement of the coupling for the supersymmetric scenario. But here I can only basically briefly comment about this picture with the top. Second, yes. So you know that if you want, you know, supersymmetry to explain the hierarchy problem, basically to explain why there is no quadratic divergences, you expect a very light stop. I mean, certainly below something like below 1 TeV, and this is already currently constrained by the direct search for the stop. So in this plot, there is the current bound on the stop coming from the direct search at ATLAS and CMS. I think this is an ATLAS plot, if I remember correctly. And now, if you have a light stop, it will also affect, of course, the decays of the X into gamma-gamma, for instance. And you can use the measurement of gamma-gamma decay rate actually to put some constraint on the top. And this is what we have reported on this plot. So here, this plot, this region is the one which is currently excluded by the measurement of the X coupling to gamma-gamma via the loop of the stop, right? And you see in particular that this region covers the region which is very delicate to access directly when the stop mass is very close to the mass of the stop. In this case, it's very difficult to disentangle the stop from the top. So there is basically no way to rule out a stop which has a mass close to the top. But indirectly, by looking at the coupling of the X, you can do that, and then it's very complementary, and you can also see how those exclusions, those indirect exclusions, will scale when the gamma-gamma rate will change with time. Okay, I wanted also to discuss the effect on the model of strong interaction, but I think I don't have time to do that. So we can go directly to the conclusion. So the conclusion is whether or not the X should have been chosen by the Time magazine to be the person of the year. And last December, actually, you could go to the website of the Time magazine and vote for the Higgs boson to be elected person of the year, right? And if you look at how the vote of the people are going at the beginning of December, it was December 6th of 2012, you see that the Higgs boson were somewhere at the rank 20 out of 40 people that were proposed. So way below this crazy Korean guy, right? Is more than 4 million of votes, but still there were many physicists voting for the Higgs particle. And actually, it's also interesting actually to see what was the motivation of Time magazine to elect the Higgs boson the person of the year. They say that last summer, a team of researchers at CERN, basically Rolf Hoyer, Joe Incandela, and Fabiola Gianotti, confirmed Einstein's general theory of relativity by finding the Higgs particle. And at the end of the day, you know, the Higgs didn't make it to the front page of Time magazine. As you know, it was Barack Obama that was elected again the person of the year, but at least Fabiola Gianotti was number 5 in this election, and she made it to the front page of Time magazine. Okay, so I think I will stop here and maybe take a few questions if we still have time. So thanks a lot for your attention.
Question? No question, no say.
So Alvaro.
Oh, Alvaro.
My microphone.
Okay, it seems to be working.
Okay.
Tu m'entends, Christophe?
Oui,
Okay.
très bien.
Coming back to, in particular, the branching ratios and the operators that play a role there.
Yes.
Sooner or later, maybe already, it would be interesting to know what the deviations from the standard model tree-level value are due to loop corrections in the standard model. Is this research completed? I'm saying that the operators are not just one in the plots that you had. It's 1 plus order alpha.
Yes.
Are the order alpha corrections
Yes.
systematically computed?
So, so there are various kind of corrections. There is alpha strong, and this you can simply rescale them from the standard model computation. So it's a very easy computation, and this is taken into account, of course. And then there is, of course, the NLO electroic correction. And these are more subtle to do because, there is some additional diagram compared to the standard model one. So the bottom line is that, yes, the NLO QCD, well, yes, in the standard model, they have been included, right? The NLO electroweak and NLO QCD.
When you have computed the branching ratios,
yes,
and compared them to experiment, that was at tree level.
yes. No. This take into account the NLO QCD and in some cases the NLO electroweak. Not all of them, but some pieces of NLO electroweak.
Now, another question is the following. When comparing spin hypotheses, it is simple and useful to test the relative likelihood of the data relative to the two hypotheses you are comparing. And that gives you a number for the confidence level of your conclusion, whatever it is. Now, in the case of branching ratios, you have something like a 5-dimensional space for a branching ratio into the various channels. But you're not comparing two hypotheses. Yet there is a way which goes beyond your 2-dimensional plots. Sometimes you show the value of one parameter relative to another, and the ellipses or whatever they are for the different results. There's a way which is a goodness of fit. And it would be interesting to know in the full 5-dimensional space how good the fit is in the sense of statistical significance. Has that been done?
It has been done not with the full 5 parameters at the same time because basically the fit doesn't really converge. But yes, looking at subclasses, 2-dimensional fit, yes, this has been done. Of course, you can really compute, the likelihood, etc. Yes, but
so
not with
a 2-dimensional plot from the number of sigmas. They're away from the central point of a standard model, but it can also be done in 5 dimensions.
But in 5 dimensions,
suppose it was. There is a meaning to the goodness of fit, depending on the distance from the central observed point, say, to the central predicted point.
Yes, but the fit will be, the likelihood will be, almost flat, in all directions. It doesn't converge. So you need to put some assumption, to put some of the coupling to the standard model value or whatever your preferred value is to make it converge.
Maybe.
So for instance, if you have a particular model.
No, I'm not talking about a particular model. I'm talking about goodness of fit.
Yeah, no, but again, if you
suppose you have the theoretical prediction for the shape of the Z peak in E plus E minus annihilation, you can tell how good the fit to the data are without invoking an alternative hypothesis. So there's a goodness of fit criterion, which is also the case for a bunch of branching ratios. There's a goodness of fit criterion.
Yes. Yeah, so you can do that if you have, 2 or 3 parameters, but at the moment you cannot do that if you have 5 because the likelihood is almost flat, and then you cannot,
It cannot be almost flat because there are hypotheses that are excluded by the observation, like all couplings are twice the standard model value. That's excluded with a lot of significance. I am only asking what is the significance with which it is excluded.
No, okay, sure. What I want to say is that there is some flat direction in this likelihood, right? That doesn't allow you to really give the goodness of fit of the standard model.
I'm not believing you. This is what you're saying, but I don't believe you.
Well, the fact, for instance, that you cannot. Yes. Okay.
Okay, those were my questions. Thank you.
Okay, thanks.
Questions? No. Yo, I think thanks, Mr. Grojean, for the nice presentations.
Okay, thanks a lot. And see you next time.
So much fall, it was too good. Ciao.
Okay. Bye-bye, thanks.